and then he will talk about singularities of minimal hypersurface and the other variational problems.
Can I also give my Chinese name?
You have a Chinese name.
Right. Okay. Okay. So I think I want to try to at least explain each word in the title. So I know if by the end of the talk everyone understands the title, I'm happy. So let's naturally work from the end and get to the beginning. So a variational problem is in general when you have a function and you're trying to find perturbations of that, you're trying to find critical points. The finite dimensional version, right, is when you have, say, a function from a certain manifold in R, and then you're trying to find critical points of this function. This is the finite dimensional variational problem. But I'm more interested in infinite dimensional variational problems. So let me give you first one example, and this is so the simplest case of minimal surfaces is the case of geodesics. A geodesic is a curve in space, say in R3, in R2, in Rn, or on a manifold, that locally, so if you look between 2 points that are very close together, the length of this little segment is equal to the distance between x and y. So in other words, among all the curves connecting x to y, this one minimizes the length. Okay, so locally, a geodesic minimizes length. So if these 2 points are very close together, any other curve connecting x to y is going to have length higher than this one. Length is, if you call this curve gamma, say parameterized from 0 to 1. So gamma is a curve from 0 to 1 into your ambient space, or it could be a manifold, it could be Rn, it could be R2, it could be R3. Okay? So locally, minimize length. But globally, if these points are too far apart, maybe I can find another curve that has less length. But globally is a critical point. What does it mean, a critical point? If I take my curve gamma and then I look at a variation of gamma, something like this, call this gamma of s, where gamma of 0 is equal to gamma. Then if I look at the length, and differentiate once, and this is equal to 0 for any variation, right? So this one called a couple of variations, right? Any variation with the endpoint fixed, then the first derivative is equal to 0. Okay, this is what it means to be a critical point of length. So globally, so from initial point to end point, critical point of length. Locally, if there's 2 points close together, is a minimizer. No? So of course, let me give some examples. If you're in a two-dimensional plane, or even Rn, any Euclidean space, the path, the shortest path between 2 points is always a straight line. If you're in a sphere, let's say S2, then parts of the equator are geodesic. So this is a geodesic connecting this point to that point behind. But of course, if you go to the South Pole first, it's a shorter path, right? So it's not a global minimizer, but of course, if you look at two points close together, it's a minimizer. Or, for example, if you look at a cone, two-dimensional cone, we remove this point. You take a point here, one geodesic goes around the cone and up, like this, connecting this point to this point. But of course, there's a shorter path, just going up the direction of the cone. Okay? So this is one variational problem. And now what I want to do is take this problem and then look at the two-dimensional version of this problem. This is the one-dimensional version, geodesics. Two-dimensional version is what we call minimal surfaces. Before I talk about the about minimal surfaces, let me first talk about the plateau problem. The problem with geodesics, I start with 2 points, and I connect these 2 points by a curve, and I try to find the curve of least length, right? The corresponding problem in higher dimension, instead of starting 2 points, I start with a certain curve, a one-dimensional object. So I push everything by one dimension. So this is a curve. And now I'm looking for a surface, sigma. The boundary of sigma is equal to gamma. And I'm trying to minimize the area of sigma with this fixed boundary. This is called plateau problems. I mean, finding a solution to this. For finding a surface, maybe I should call this X. Finding a surface whose area is the least among all surfaces with this fixed boundary. Okay. Maybe I should do some examples. First, say you have a disk. So I'm in R3. This is some plane, some R2 plane, and this is a round circle. The solution to the plateau problem here is just a disk. So this is the surface of least area whose boundary is this given circle. This is the isoperimetric inequality. Okay. What if I have two disks? This curve can be disconnected, right? I always draw them connected, but it could be just two curves. So say you have two curves. Two circles. What is the least area surface whose boundary is the union of these two circles? So here, there's two situations. If the two circles are very close together, then you can find an annulus here that connects these two that have least area. If the two surfaces are very far apart, the annulus has very large area compared to just the union of two disks, right? So this is not the solution. The solution is just the union of two disks, because the union of two disks is a fixed area. So if I go very far apart, the neck becomes very large area. But if they're very close together, the next very small area, right? So this one can change. So you can see even for the same curve essentially could have different solutions, right? So of course, at some point, the area of the neck is going to be equal to the area of the two disks. So then you have actually two solutions, right? So this problem has no unique solution, unlike the geodesic case. If you're very close together, there's only one minimizing geodesic. And the third one is a picture that is very difficult for me to draw, but it's something like this. Some curve like this, and then the solution to this one is a torus minus a disk topologically. It's difficult to picture this, but it's going to be some kind of torus. Depends on the shape, right? I didn't draw it perfectly, but there's a certain shape that the solution is a part, and it looks more or less like this.
So the curve is still unknotted.
Unknotted, yeah. The one is just think like a disc, and then you bend it's a wire. No? You bend the wire inside itself, but it's unknotted. Yeah. It could be knotted. You could say something it's knotted. Yeah. It's just more difficult to draw.
A minimal surface.
Yes, you can always find a solution. Yeah. You can always find a solution for any curve, but the solution might be good or not, and then it depends. And okay, so this is the two-dimensional, and if you want to go higher dimensions, then your gamma. Now we're going to use a capital gamma, right? So if the dimension ambient, if your ambient space, so say you're in Rn plus 1, now the same problem when you look at gamma is a n minus 1 dimensional, n minus 1 submanifold, and then you're looking at sigma is a n submanifold, hypersurface, no? And the boundary of sigma is n minus 1. So you start with this submanifold, and you're trying to find sigma. You fix the boundary, and then you minimize the area, but now it's n-dimensional area. So it's essentially the same problem. It's just a bit more difficult to draw pictures, huh? Okay. And these solutions, they are minimal surfaces with boundary. Okay. So now let's see what is a minimal surface. Or rather, minimal hypersurface. Hypersurface is the codimension 1 submanifold. So it's really like this. Could be Rn plus 1, but it could be ambient space, could be a manifold as well. So minimal hypersurface, similar to a geodesic, locally minimizes area, so solves plateau problem. And globally, again, critical point of areas. So if you start with a surface sigma, this is let's say it's two-dimensional, okay? And then you push perturb sigma s. So in general, sigma s is just p plus a vector. Let's say we are in R3. This is two-dimensional. X is just a vector field in R3. So I just look at each point here, I push in the direction of x, this is my sigma s, and then push with speed s. With the s measures how much I'm pushing. So this is a variation of my sigma. So critical points, again, the derivative is equal to 0 for any vector field you choose. Okay? Maybe we should say compactly supported. Compactly supported vector field. If the surface is not compact, which can happen, then it's not so clear how to differentiate things or how to solve this. Okay. Any questions? Okay. So I'm presenting minimal surfaces from a variational point of view, but you can do it from a more geometric point of view. But I think for the purpose of the end of the talk, I think it's not worth spending too much time on the geometric perspective. But locally, every surface, if you take a point P, if you look at the tangent plane of your surface, locally, the surface is just, this is a ball of radius epsilon. Locally, the surface is just a graph of a function u defined on your tangent plane. Okay? And this first variation, this first derivative, is going to give us a PDE for our graph. The PDE looks like this. Divergence of gradient normalized this number equal to this. This is called the minimal surface equation, or the graphical minimal surface equation. So locally, every minimal surface solves this equation, as long as they're smooth, or at least say C2. Okay, so you can differentiate things twice. Or even if they're not C2, you can say solve this PDE in a weak sense. Oh, I erased the title. No. Okay. The last word is singularity. Okay. So what's important from this PDE is if my u from classical PDE theory, if my function is a little bit regular, then I can actually force my solution to be smooth. Okay. So every time I talk about smooth surfaces, it's because as long as my U is even just a little bit regular, I can get smoothness. So when we're talking about singularity, singularity can have different meanings in different areas of mathematics, right? And if you're trying to find functions of class C3, a function of class C2 is singular, right? Because it's not C3. Right? So singularity really depends on what you're looking for. And I'm interested in finding smooth solutions of smooth solutions, and in my case, I'm more interested in surfaces that are embedded. So I'm not allowing self-intersections on my surfaces. They have to be embedded. They cannot touch, self-touch, right? At least for minimal surface. Things like this, not interesting for me, at least for now. So, and like I said, even a little bit of regularity gives me smoothness. So a singular point is something that is very, very not regular, something that I can't differentiate at all, and I cannot represent by anything embedded. I'll give you a picture instead of defining what's a singular point. I'll just give you a few examples and give you the sort of toy model for a singular point. First is the plane, say a two-dimensional plane in R3. It's a minimal surface. Okay. If you look, always solves the plateau problem, right? Any flat curve, the solution is always just whatever disk that contains that's inside the curve, right? Another example is called a catenoid. Looks like a little bit like this. And I also locally solve the plateau problem. If you look at a very small neighborhood around the neck here, you remember one of the plateau problems I gave you. This is the solution. Of course, if you look at if you increase the size of this neighborhood, then the catenoid doesn't solve the plateau problem anymore. But then if I take a point over here and then I look at a small neighborhood, it's going to solve, right? So the size of the neighborhood depends on the point. The size of the neighborhood where the minimal surface solves the plateau problem. In here, it solves everywhere. Any ball you take is always going to solve the plateau problem. No? It's a very special case. Let's say in say your S3, so the three-dimensional sphere, and then your surface is just the equator, S2. This is the minimal surface. If this one's less obvious, but if you think of the geodesic case in S2, it's the same population. Three, four. Okay, this one is impossible for me to draw, but let's call this sigma. So it's x, y in R4. So this sigma is in S3, right? S3 is inside of R4, S3 of radius 1, and of course if you add this one, you get 1, so it's in S3, and it's, I'm not going to try to draw it, but it's some torus inside R4. This is called a Clifford torus. And it's also very important minimal surface in S3. let's see, 5. Let's see, your first example was singular one. If you take the cone over this example, so this is lambda times p. P belongs to sigma. Lambda is greater than 0, greater or equal than 0. This is a cone, looks like this, and it's singular at the origin, right? The cross section of this cone is cross section of the link is a Clifford torus. So it doesn't really look like this, right? It's not. The cross section of torus, not very contrast. So this is a three-dimensional minimal hypersurface in R4 with one singular point. Of course, you cannot make this regular, right? And the higher dimensional version of this one, that would be, let's call it C. That would be X, Y in R4 cross R4, so in R8. But the size of X and Y are the same. They're not fixed, they're not equal to 1, right? They could be anything. So no, it's a cone, right? Of course, this is a cone, right? If you change X and Y by lambda X lambda Y, then still inside the set cone. So this is called a Simon's cone. And the 7-dimensional minimal in R. Oh, right. Okay. Okay. And again, singular, no? But I'm going to see in a moment this singular point, this singular minimal surface, and this singular minimal surface are very different.
So, just curious, if for Clifford torus, one of the number is slightly less than 1/2 and the other is slightly greater than 1/2, is the surface still minimal?
No. It has to be equal. Yeah. In here, you see this one is the link is also torus. Not really at all, but we also call it Clifford torus. So the link is S3 cross S3. In here, if you change these dimensions and you change the radius appropriately, it is a minimal surface. But just changing the radius and not a minimal surface anymore. Yeah. But here you can have something like this cross S4. But I don't remember what's the radius. Yeah, I don't quite remember. But this is also minimal surface. But then the radius is now 1/2, 1/2 square root 2. And I guess your question is also similar to here, right? If you change the radius of this S2, imagine the geodesic is like shrinking a little bit, moving from the equator to something that is not equator anymore, then it's not a minimal surface, right? So the Clifford torus is the same idea. If you start shrinking one side and enlarging the other, it's not a minimal surface anymore.
And it's actually maximum?
Clifford
torus.
Maximum in which sense?
The area.
So we'll talk about that now. Yeah. So in the sphere there's no minimizer, right? Because you can always take a very small circle to a very small area. So you're never going to find a minimizer. So this one is unstable in the sense that it's not minimizer, not even locally, and this one is also unstable. Yeah. if you look at the variation that corresponds to enlarging and shrinking the radius, I'm not sure if that's a variation that decreases area or not. That's not. I have to think about it. That's not clear. It could be, but it's not clear. Yeah. Right. So. Okay. So we look at the surfaces, and we know this, right? But from the variation perspective, if I differentiate this again, then what I get is the quadratic form. We know the linear algebra quadratic form that depends on that initial vector field, that initial speed that I'm pushing my surface, right? So this is, just think of a bilinear form in the space of vector fields. Okay, the space of vector fields is a vector space. You add two vectors fields, you get a vector field. So it's a bilinear form. And in here, in this, the formula is not important for now, but it's a bilinear form, quadratic form. Huh? Then you can define the index of this form, and then the index of sigma is just the index of this quadratic form. That is just the maximal dimensional plane. So the maximal dimension of the plane, so this quadratic form is negative definite. So if I take a plane in the space of vector fields, no? And in the space of all vector fields, I take a plane in this space. Any x that I put here is going to be negative. So this is just the second variation, right? If you look at the Taylor expansion of the area functional, right? If you have a critical point, the Taylor expansion is going to be the area. The first term is 0, and then the second term is this quadratic form. Okay. So this, if this is always greater or equal than 0, I say that the index is 0, right, because there's no plane that makes it negative. So this is a local minimizer. If this is less than 0 for certain planes, then there's certain direction that I can push my surface. Right? This is the direction I'm pushing my surface. There are certain directions that I can decrease area. Does that make sense? Plus, I guess, a little o of x squared. No? Okay? So I'm just looking at the Taylor expansion of area. And this is what I call the Morse index. This is called the Morse index of sigma. And it goes back to your question about this the Clifford torus, right? So before I get there, let's look at the plane. The plane is stable. Stable means index equal to 0. So any perturbation that I push here, the area is going to increase. Okay? Of course, the area of the plane is infinite, so when I talk about perturbation, I'm talking about perturbations inside a compact set. Right? So inside a compact set, any perturbation is going to increase area, because the second variation always non-negative. This one has index 1. So there's one direction that I can decrease area, and all other directions are going to increase area. Okay? This one, the index is equal to 1. So in here the direction is very clear. I just push perpendicular to the equator, right? Just like a rubber band on a ball. if you put the rubber band at the equator, the length is very large. If you push a little bit, the length shrinks. Same for the area is going to shrink. So the direction is just perpendicular to S2. And here the index is equal to 5. It's difficult to explain what's the directions here, and to not answer your question originally, I know there are 5 directions that decrease area. The direction corresponding to shrinking the annulus and shrinking one side and increasing the other could be a linear combination of these, some of these 5 directions. So it's not clear to me. That's why I don't know the answer. Right? I know it's not any of these directions because I know what all the directions are, but it could be a combination. Right? So it's I don't know the answer, but I'm sure someone knows.
So how do you know the 5?
The 5. Oh, it's a paper. Huh? There's a very clear proof. You can say explicitly what the directions are, because I think, if I'm not mistaken, it's rotation, all the possible rotations. There's a 4, and then the 5th. Now the 5th I don't remember what it is, but the 4 rotations. Right, so you fix the plane, rotate around each step. There are 4 directions, right? You're in R4. There are 4 coordinates, so there are 4 coordinate lines. So rotating around each coordinate line. No, wait, not rotating, pushing around this coordinate line, pushing the direction of the coordinate line. So if you have your coordinate direction, pushing in this direction shrinks. Yeah. For each direction. In here, there's only one direction you can shrink, right? Only the perpendicular one. Yeah. But for this one, you have all 4, and then the 5th one I don't remember. So, it's a paper by Urban. 94? 94? 90, somewhere in 90. And turns out this is actually the only minimal torus in S3. This is a result by Simon Brendel very recently. Yeah, I think it's very interesting. So any other torus that is not this one, is not minimal. Now this one, the index of this minimal surface is actually infinite. So the index could be infinite, right? There's one example I didn't give here. It's called a helicoid. So the helicoid is just imagine you have a line, and then you rotate this line and push down at the same time, or reversely push up, and you look at the image that you create from doing this. That's the helicoid. This one also has infinite index. But in this case, the index is infinite, meaning there are infinitely many directions I can decrease area because it has a singular point. Okay? The singularity forces the index to be infinite. In this case, but now in this one, the index is actually 0. And that's the key point why that's the key observation for why people are interested in studying singularities of minimal surfaces. Up to dimension ambient dimensional 7, singularities mean that you have infinite index. But as soon as you cross from dimension 7 to 8, you can have something stable that has singular points. And maybe I should make an observation here. The index of a cone is either 0 or infinity. Because, let's pretend the index is equal to 1. So it means that I have a compactly supported vector field that pushes my area, that decreases my area, right? So say this is the support of my vector field. Then if I take this vector field and just translate and readjust, I can push this vector field to the same vector field but now supported here by just using the conical structure, right? But now this vector field and this one have disjoint support. They both decrease area and they have disjoint support, so they're linear independent. So actually I'm saying, oh, the index is 2. I do it again, I push a little bit more. The index is 3. Right? So if the index is not 0, I can construct infinitely many linearly independent vector fields that decrease area by just using the conical structure, right? So this is a very interesting but simple observation that the index of a cone is either 0 or infinity. Maybe this is very obvious for you, but for me it took me a long time to understand this. Okay, so let me talk about regularity. So there's a result by Pitt 76, Shen-Simon 81, and Fica massa que era 2003. 2009, sorry, 2009. It says the following: if you take sigma, let's say in Rn, okay, Rn plus 1, doesn't have to be 1. It's minimal and stable. Then, if the dimension is between 2 and 6, sigma is smooth. If the dimension is 7, then the set of singular points are all the points where sigma is not smooth. Okay. Sorry, there's one more assumption. And I'll say something about this in a second. If n equals to 7, the singular point is all the points where sigma is not embedded and not smooth. Okay. Either not embedded or smooth. So regular points are points where locally it's an embedding. So this is isolated points. And then 3. Then the best you can get at this until 2009 is that the dimension, called the Hausdorff dimension of a singular set, is at most n minus 2. Okay. So this condition is just saying I'm looking at surfaces that are not immersed. Okay. So it's a little bit more than that, but I don't want to get too technical. But essentially, I don't allow immersions. I don't allow self-intersections. I also don't allow, for example, things that look like a union of 3 planes, hyperplanes. Okay. So I don't allow self-intersections. I don't allow locally things that look like union of three planes.
So that notation means house of measure.
This H is called the house of measure, yes, and this is the dimension with respect to the house of measure. But instead of defining what it is, let me just give some examples. One of my teachers, 12 years ago at university, he said that the way to define manifolds that he learned from Manfredo do Carmo, you define manifolds like this: plane is a manifold, the sphere is a manifold, M is a manifold. So just give a couple of examples and hope that people understand. So what is the Hausdorff dimension? Points have dimension 0. Okay? So if you have a countable set of points, then the dimension is equal to 0. Okay? If you have a curve, a rectifiable curve, so a curve that you can measure length, countably rectifiable curve, so just a countable union of regular curves. It's called countably rectifiable. And the dimension is equal to 1. And one more example, the space filling curve. The what's called piano curve, I think it's called. The curve that covers the whole of the square. The dimension is equal to 2. Okay, it's equal to whatever it's covering, right? Whatever space is filling. So if it's in R2, it's going to be 2. If it's not N, it's going to be N. Okay. So the Hausdorff dimension is a way to measure the dimension of a set. Let me just leave with these examples and then talk about this. You can see here why this one has index infinity, right? Like I said, it's either 0 or infinity, but this situation here, I mean the first case, dimension is low. So everything that is stable has to be smooth. So this one cannot be stable, has to have the infinity index. Now here, I'm past the smooth dimension. I'm in dimension 7, right? My cone has dimension 7. And this is showing exactly that this result is sharp. Right? You have a stable means index 0, stable minimal surface with one singular point. Okay? Okay. Any questions so far? Right. So this result is also true, I should say here. Also true for index finite. So if you know that the index is finite, you can get the same result. Okay. Now, this result was improved by Neighbor Torta in is the end? Okay. In 2015. So the only improvement, nothing you can improve here, right? Just smooth. The improvement comes from here, how to control your singular set. So if you have all the same hypotheses, and you have, instead of stable, you have area minimizing. Then, and I'm assuming n is greater or equal than 7. Yeah, let's say n is greater or equal than 8. Okay. Then, what they prove is that first, the singular set is rectifiable. This is a very strong statement. And they also say that now I'm going to, that is the Hausdorff dimension, this is the Minkowski dimension, is at most n minus 7. So they improve the dimension. Okay, well, I don't know what that is. That doesn't mean anything. Again, let me give some examples. And then, so first of all, the Hausdorff dimension is smaller or equal to the Minkowski dimension. You can see right away it is an improvement, right? If I get upper estimates for this one, it's stronger than getting upper estimates for this one. Okay? For example, if you take in the plane the countable dense set. Countable means Hausdorff dimension is 0. Dense in the plane in R2 means that the Minkowski dimension is 2. Even if you don't know what it is, believe me. Okay? So in many situations, this one is strictly larger. If you have a curve, then the dimension something regular, then the dimension is equal. Of course, in some situations it's equal. Otherwise, it's say it's strictly smaller. But there is one more example I want right here. You have this curve. So the sine of 1 over x, the graph of this curve between 0 and 1, strictly between 0 and 1. Here, this is a rectifiable curve, right? So it's a union, it's a countable union of smooth curves, right? You can always put countably many smooth curves here. So the Hausdorff dimension is equal to 1. The Minkowski dimension is equal to, I think, 3 over 2. These dimensions could be, they don't have to be integer. Okay, also in this situation, so the new result rules out, for example, this type of singularities. They're terrible, they're dense. Rules out singularities are accumulating on a certain part of itself, right? So it's significantly stronger because it does rule out the very bad behaved singularities. So to finish, you say a lot of other people's results. I should say something about my results. So, what I did together with Sean McCurdy and Paul Minter, and I guess this was published last year, is that we took this result and we first we proved the same result, but instead of area minimizing, we did exactly the same as that one. We changed it to stable. So we can improve this to stable. Or we did more. We did index bounded, and then we get the same result. This kind of dimension. And I think what's interesting here is that the method that we did that we, first of all, we have to prove if we're stable. This is a very important part. But then everything else of the proof has nothing to do with minimal surfaces. It's all the idea is just to take our surface and somehow we can find a finite covering by stable sets. So locally things are stable. Not minimizing anymore, but stable. And once I have a finite covering by stable, you take a surface, right? Take a surface sigma, and I take a ball and say it's stable here if every variation, the second derivative, any vector field that's supported in here is zero, right? It's greater than 0. So I can cover by a finite number of stable. We did more than just this, but by a finite number of stable solutions, then I can apply the stable results, right? So what I think is interesting is that the method works for any variational problem, not just minimal surfaces, because it's only a matter of taking, I understand the stable solutions. I have any property on stable solutions, I can push this property to anything of finite index. So give me any variational problem, and you say, okay, I know every stable solution has this property, property X. And this method, I can say, okay, if you know that, then by this argument, any finite index solution also has property X, right? Okay, so I guess I'm trying to sell on the method without even telling you what it is. But the result is here. And the number of coverings that I get is completely controlled by the index, explicitly controlled by the index. So it's the number of balls is a constant times index plus 1. So we know it's quite interesting. And then in a coming paper we're going to do the same for a different variational problem. As we're going to do the same result for any prescribed mean curvature. So you give me any function, you give me a surface with that mean curvature, and I can give you the same result. Mean curvature is the geometric interpretation of the minimal surface, right? Mean curvature equal to 0 is minimal. I think that the next result that we're doing should be coming out this year. You can do the same for any prescribed mean curvature, any function. C1 alpha, any function could be, doesn't even have to be super regular. Right, guess I'll finish here. Thank you.
Any questions? I'm trying to get some intuition about the Minkowski dimension. So let's consider a set and its closure. Do they have the same Minkowski dimension?
What is the set?
The set and its closure.
Yeah.
They have the same.
Yeah. Because the Minkowski dimension is about you take a set and you look at a covering by balls, right? So if you take the closure, the covering is going to be the same. And then you cover by balls and you let these balls tend to 0 with a certain power. So you take the volume of these balls with radius r, and then you take n minus alpha here. So if you let r tend to 0, this number is going to go either to 0 or to infinity, for depending on alpha, right? And then that's going to be your dimension. So if you take the closure, the covering by balls is going to be the same. So yeah.
And this is not true for Hausdorff dimension.
No. Yeah. You take a dense set, right? Dense set. Hausdorff dimension it's our intrinsic. It's looking at diameter by intrinsic diameter, and this is our extrinsic measurement. So if you look at a submanifold, look at submanifold dimension K. The cross section, everything is outside is going to be dimension n minus k. Right. So when you take a covering, this power here they're going to use is going to be n minus k.
So you mean this dimension depends on how you inflate this submanifold into
yeah.
thing, right?
Yeah. Well, it doesn't depend on the embedding, because if it's a smooth dimension, it's a surface of dimension k, it's going to be k.
Okay.
If it's something regular, the dimension will always coincide. But in this picture, right, it's something that is dimension 1,
Yeah.
but the Minkowski dimension is not, because it's accumulating on itself, right? It's not proper,
Okay.
right? If it's a proper, then yeah, it's okay. But even if it does something like this, it's still dimension, in this picture, dimension 1, right? It depends on how it accumulates, right? This one accumulates very densely on itself, or on a certain part. So yeah, the closure is going to have the same dimension. Yeah. I think more important than the definition is really really this picture and the dense number of points, right? So there is a strong improvement. So that theorem allows for a dense set of singular points, and that's terrible, right? If you want to talk about anything as somewhat regular, at least you need a little bit of space for regularity, huh?
Yeah.
And that one doesn't say that, but this one does. Right? You always have a little bit of space to do whatever calculations you need to do. Right?
So when you define index, you look at negative direction. Are those should those come from the formation of complex support?
That's right. So ambient deformations from complex support.
So even if your deformation decay rapidly at infinity, you do not count.
No.
Do you miss?
You can count those.
Yeah, but do you miss something?
No.
No.
If you do count those, then you get some stronger estimates. So
Is the index the same or what's different?
you could count those as long as your surface is well behaved, and then it doesn't change the index. Okay. Yeah. So it doesn't. But
I want some
yeah.
more careful.
That's right. So for any given minimal surface, if it's not properly embedded, if it's not complete, then it could change. But if it's complete, properly embedded or properly immersed, then it shouldn't change. You could consider, I guess, any W12 vector field. Yeah. Actually, you don't even need to really look at vector fields, you only look at functions, because I'm looking at codimension 1. So any vector field that pushes in the tangent direction is just going to take my surface and reparameterize. So I only care about normal direction. So if I take a normalized vector, say it's two-sided, then all vector fields that are interesting are f times n. So in the end, it's just the PDE. That's the q of xx is just the q of f, and then this is a differential equation. Well, not equation because I didn't put equal to 0, but it's a differential operator on f. And then that differential operator is well defined as long as f is in W12. So you can consider more. And if the function is well behaved, then the extension of this operator, and then you can talk about, there's an operator, so you can talk about the spectrum of this operator, and then you can talk about the number of negative eigenvalues, right, as an operator on W12 functions. So I try to put it this way because it's more visual. When you start talking about the PDE, it's a bit more complicated, but yeah. And you can even further extend to other weighted spaces, and then you get a little bit more information on your index. Right? Depending on what kind of weighted space you're working on, you can get more information on the index. Some people have used this to relate the index with the topology of your manifold. So if you allow for certain weights, you can count the ends of the surface. They end up contributing to index, right? Because you can get certain functions, a certain decay, that are going to be eigenfunctions for this eigenfunctions for this operator for negative eigenvalues. Then you can find more eigenfunctions depending on the number of ends. Yeah.
So for minimal surface like this with singularity, the local area is still finite, right? Or
Yeah, it's finite.
So this is of course different from like vortices or monopoles where the local energy is already infinite. Do you see mathematically how the difference comes about from the equation?
There's actually a connection of vortices and minimal surfaces, and even monopoles and minimal surfaces. I mean, the fact that the area is finite is somewhat trivial, because the area is just I'm just taking measure,
Yeah.
right? So if you take a Lebesgue measure and then you remove a point, it doesn't change anything, right? So essentially, it comes a little bit from the fact that I am already assuming that the singular set is somewhat small.
Yeah, but I want to look at it from the point of view of PDE.
Right.
Yeah. So you see, in electromagnetism, you cannot do that. You take away and
Right.
there be a singularity, then the energy is infinite. So what is the equation, the property of the equation for?
Well, I think it's not just the equation, but it's the functional. The function doesn't care about energy, but the area doesn't care about derivatives. Right?
Well, it has.
Yeah.
Well, it certainly depends on system. But suppose you put the energy of harmonic mass.
Right.
This is still finite, locally finite energy, right? Or is it not?
Then no. If you
No.
look, no. Yeah. So harmonic maps. The image of a harmonic map, say if I have a harmonic map from S2 into some three-dimensional manifold, the image is going to be a minimal surface. We would call a branch minimal surface. There are certain branching, and in those points the area is not finite, right? That's where the energy could blow up, right? So there's a correspondence between harmonic maps and minimal surface, but then you allow for singularities that are a little bit different from this singularity. Again, singularity depends on what context. The word singularity doesn't mean anything. In our context, I'm asking a lot. Essentially, is what do I mean by regular? And I'm asking a lot for regular. And here, regular is a little bit less, right? So if I ask less for regular, then singularity could be a little bit bigger. Could be contribute to the energy. Yeah.
Any other questions? No, that's